All right, so I am going to explain how you can use the no-growth isocline models to predict the outcome of competition for two species. So let's take a look at species one, the graph of species one. So on the x-axis, we have species one, and on the y-axis, we have species two. Remember that it always goes in that order where species one is on the x-axis and species two is on the y-axis. And so using the carrying capacities and the alphas, so the competition coefficients for the two species, you can plot the endpoints of this no-growth isocline. So remember K1, that's the carrying capacity of species 1, and K1 over alpha 1, 2 is essentially the conversion for how many species of species 1 could be carried in the carrying capacity of species 2. So those are the ends of your no-growth isocline, and then anywhere along this isocline, any population densities or combinations of population densities of species 1 and 2, there's no growth of species 1. So this is dn dt equals 0 along this line. So anywhere to the right here, any population densities that occur to the right here, the population is going to, of species 1 is going to shrink. So we are above the no-growth isocline of species 1, which means that the population is going to shrink. So that is represented by these arrows here that are parallel to the x-axis and represents the population of species 1 decreasing. And anywhere to the left of this line, we're below the no-growth isocline, which means that the population of species 1 can increase. So any population densities that occur below the no-growth isocline, mean that the population of species 1 can increase, represented by these arrows, and anytime there's a population density above this no-growth isocline, that means the population of species 1 is going to decrease. And along this line is exactly where there's no growth. So we can take a look at species 2. Again, species 2 is going to have a no-growth isocline. We can plot the ends of species 2 using the carrying capacity of species 2 along the y-axis and the K2 divided by alpha 2, 1 on the x-axis. So remember, that is essentially representative of how many species of species 2 are going to fill the carrying capacity of species 1. And we have a no-growth isocline for species 2 here. So any population densities along that line are going to represent dn dt equals 0 for species 2. So just like species 1, any population densities above this line mean that the population of species 2 is going to shrink, represented by these lines here that are parallel to the y-axis, showing a decrease in population size for species 2. And anywhere below the no-growth isocline means the population can increase. So anytime we're above the no-growth isocline for either species, that means the population is going to shrink. If we're below it, that means the population can increase. So now we can put them on the same line, and we can use these no-growth isoclines to determine the outcome of competition. So here we have a no-growth isocline for species 1, so shown here dn1 over dt is 0, and here is our no-growth isocline for species 2. So this is dn2 dt equals 0. So this is the no-growth isocline for species 1, this is the no-growth isocline for species 2. So we can go through some examples to understand how the population densities of both species is going to change based on a starting density and based on the no-growth isoclines. So if we were to start with a population density here, so this n1 comma n2 represents just a combination of population densities of species 1 and species 2. So if we start at a no-growth isocline, if we start at a population density here, we are above both of the no-growth isoclines for both species. So that means that population growth for both species is going to be negative. So what's going to happen is that the population will shrink, and it will shrink until it hits the no-growth isocline of species 1. And once it hits this no-growth isocline of species 1, we're still above the no-growth isocline of species 2, which means that the population of species 2 has to shrink. So what happens is the population of species 2 starts to decrease because we're above the no-growth isocline, and as it's decreasing, that means that it's freeing up resources and population 1 can grow. So what's going to happen is as the population of species 2 is decreasing, that frees up resources for the population of species 1 to start growing. So species 1 is going to grow along this no-growth isocline until it hits its carrying capacity. So as species 2 is decreasing, species 1 is going to start using those resources to increase its carrying capacity. It's going to increase its population size until it reaches its carrying capacity. So the population growth is going to start here, and we can use the arrows to represent the growth of the two species. So again, we're outside of the no-growth isocline. We're above the no-growth isocline for both species, which means that species 2, represented by this arrow here along the y-axis, is going to decrease. And also species 1 is going to decrease, represented by this arrow along the x-axis. So we can see how that blue dot is going to move. So like I just said, it's going to move down because both species are decreasing in size until it hits the no-growth isocline of species 1. And once it hits that no-growth isocline, we're still above the no-growth isocline for species 2, which means, like I said, species 2 cannot increase, so it's going to decrease. And as species 2 is decreasing, that means species 1 can start growing, and it's going to grow until it reaches its carrying capacity. So in this instance, species 1 can completely outcompete species 2. So the no-growth isocline is, for species 1 is higher than species 2, so the stable equilibrium point will be the carrying capacity of species 1. So the equilibrium point is K1. Species 1 wins because its no-growth isocline is above species 2, and species 2 cannot exclude species 1 because anywhere along this no-growth isocline is above the no-growth isocline for species 2. So anywhere along this no-growth isocline, the growth rate will be negative for species 2. Okay, so we can use that same logic to understand how the population sizes will change based on wherever we put that starting position. So, for example, if we start our population size at a small population size of species 1 and of species 2, we're below the no-growth isocline for both species, which means that both species can grow. So species 2 can grow, represented by this vertical arrow, and species 1 can grow, represented by this horizontal arrow, because we're below the no-growth isocline for both species. So what's going to happen is that the species will both be growing, and it'll grow until it hits the no-growth isocline of species 2. And in this case, now species 2 cannot increase anymore because we're at its no-growth isocline, but what can happen is we're still below the no-growth isocline of species 1, which means that species 1 can continue to grow, and as we move up into this direction, we're above the no-growth isocline for species 2, so it has to shrink, and as the population size of species 2 is shrinking, species 1 can grow and fill those, start using the resources and grow to its carrying capacity. So in this instance, both species will be able to grow, but species 1 will be able to grow further than species 2, and eventually it will reach its carrying capacity and completely outcompete species 2. So that is what the population will do if our population densities were to start at this point here. Okay, so what happens if we start in between these no-growth isoclines? Well, what's going to happen if we start at a population density of species 1 here and species 2 here is that we are above the no-growth isocline for species 2, but we're below the no-growth isocline for species 1. So what is going to happen is that species 1 will be able to increase because we're below its no-growth isocline, but species 2 will have to decrease. So that means that our population will grow to the carrying capacity of species 1 again.